This is the second section of chapter 7, which is about methods in calculus. And we're going to be looking at L'Hopital's rule. Now, this is all to do with finding the limits of functions. Now, we've already looked at the limits of functions in chapter 6 of FP1, and I'll put a link to it in the description. And we use the algebra of limits to find the limits of functions. And in some cases where we had, let's say, sine x or cos x or log x, for example, etc. Okay, we used a Taylor expansion, or we replaced it with a Taylor expansion about a, and a would be the limit of that function. So we were looking at things like this as x tends to a. Okay, and that's what we did in chapter 6. Now, that's not always possible, and sometimes it's easier to work out the limit of a function using L'Hopital's rule. So we're going to look at what's needed for us to be able to apply this rule. So this is all about finding the limits of a function. Right, so the first thing that it must have, a function must have, is that we must be able to write the function in the form f of x over g of x. Okay, so we must be able to write it basically like a fraction, basically. So that's the first feature a function must have. Secondly, we must be able to differentiate both those functions. So we must be able to find f of x and g of x. And I'll just put in brackets here. Sometimes it may be that we need to differentiate twice. So I'll just put f double dash of x d double dash of x. So we need to be able to differentiate this function. Also, this function f of x over g of x must be indeterminate. Now, what that basically means is this. So what does an indeterminate mean? Right, so let's say we were evaluating the limit as x tends to a of f of x over g of x. Right, it's indeterminate when, if we evaluate that, we get 0 over 0, or what it tends to is positive or negative infinity over positive or negative infinity. Now, there are other indeterminate forms, but these are the two that allow us to apply L'Hopital's rule. Okay, rule. So what can we write down here? So we can only apply, not L'Hopital, but L'Hopital's rule if we have these indeterminate forms. So no other indeterminate forms are allowed. Okay, now what does his rule says now? So if all of these things are satisfied, so the function can be written as f of x over g of x, a function over function. If we are able to differentiate those functions, and if the original function that we're trying to find the limits of, and I suppose I should write it down here, we're trying to find the limits of this function here, like this. Yeah, so if it's in indeterminate form, so when we find the limit as x tends to a, whatever a is, 1, 0, infinity, or whatever, we get either 0 over 0 or positive or negative infinity over infinity. Then we can apply his rule, and his rule says this, that if this is what we're trying to find, so the limit of this quotient, that is actually equal to the limit of their derivatives. So the limit of the derivatives. Yeah. Now it may be that we calculate this, and this is in indeterminate form. So what if this is indeterminate? In other words, we end up getting 0 over 0 or infinity over infinity as x tends to the value of a. Well, we can apply L'Hopital's rule again. So here we've applied the rule. So I'll just put L'Hop or L'Hos, and we're going to apply it again. And we can find the limit of the second derivatives. And it can be applied for, again, as long as all of the rules are satisfied. So if we get to this point and we find this is indeterminate, we get 0 over 0 or infinity over infinity, and these functions can be differentiated, then we can differentiate these again, as long as we can write it as a quotient, a fraction, and then we can work out the limit of this. And again, if this was indeterminate, we could differentiate again, but often we'll find that the first or second application of L'Hopital's rule, we will evaluate the limit. So there's one little rule that's quite useful to remember, and that's this rule here. So the limit as x tends to a of e to a function of x. Okay, this is equal to e to the power of the limit as x tends to a of f of x. Yeah, so remember this. That is useful. It's not in the formula book, but one way of remembering it is that this part here basically just moves to here, doesn't it? Yeah, that's all that's happened. And I suppose you could do the same in reverse, is that you could say, right, okay, that this part here gets moved to here. Yeah, and I think one of the examples we're doing, we're going to be using that to help us evaluate a limit. Okay, so here it says calculate the limit as x tends to 0 of sine x over x. So the first thing we need to do and decide is find out if this is indeterminate. So do we end up getting 0 over 0 or plus or minus infinity over infinity as in this case x tends to 0. So we need to look at the numerator and denominator separately. So first of all, let's look at the numerator. As x tends to 0 of sine x, what will happen? Well, that will tend to sine 0, and sine 0 we know is 0, so we know that the numerator is indeterminate. Okay, so let's look at the denominator. So the limit as x tends to 0 of x, well, I think that's pretty obvious. That's just going to tend to 0. So that means that sine x over x as the limit of x tends to 0 is indeterminate. So we can apply L'Hopital's rule. So you must always carry out that test before. Don't just start using it. You must do that indeterminate check beforehand. Right, so because we end up with this, don't we? End up with 0 over 0, like this is indeterminate, so we can apply his rule, which means actually now this limit that we're trying to find, sine x over x, is equal to finding the limit of the derivatives of those. So sine x differentiated becomes cos x, and then x differentiated just becomes 1. So the question now becomes evaluating this. So cos 0 is 1, and then we just have 1 at the bottom, so it's just 1. So we can probably finish it off by saying, so the limit as x tends to 0 of sine x over x equals 1, and that's done. Okay, so in this one, calculate the limit as x tends to 0 of 1 minus cos x over x squared. So step number 1, determine whether the numerator and denominator are indeterminate. So let's start with the numerator. So the limit as x tends to 0 of 1 minus cos x, well, what happens is that will be 1 minus cos 0. Cos 0 is 1, so it's 1 minus 1, so we end up with 0 in the numerator. That tends to 0. And the limit of the denominator of x squared as x tends to 0, well, that will just be 0 squared, which is a 0. Okay, so the whole expression tends to 0 over 0. So we'll just write that down. So since the limit as x tends to 0 of 1 minus cos x over x squared equals 0 over 0, we can apply L'Hopital's rule. Right, so that means differentiating the top and differentiating the bottom. So the original question now becomes this, equal to the derivatives of them. Whoops, I differentiated even before I'd got there. Right, so the limit as x tends to 0, so the numerator differentiated will just become sine x. The bottom differentiated will become 2x. So now we evaluate what happens as x tends to 0. Now it could be that this is also indeterminate. So let's have a look what happens. So I think it is. So as x tends to 0, this will be sine 0 over 2 times 0. So this is also indeterminate. Okay, so we could say since this limit is indeterminate, so sine x over 2x, we can apply, and we can differentiate both of those again. So L'Hopital's rule a second time. Okay, so the question now becomes the limit of these second derivatives. So we're now going to differentiate the top and the bottom of this. So this is what's going to end up down here. So sine x differentiated becomes cos x, and 2x differentiated just becomes 2. So the limit as x tends to 0 will be cos 0 over 2. Cos 0 is 1. So we end up with a half. So to finish off the question, we can say, therefore, the limit as x tends to 0 of 1 minus cos x over x squared equals a half. So in this example, we applied L'Hopital's rule a second time because after the first application, the function was still indeterminate, 0 over 0. So then we applied a second time, and that allowed us to find the limit of the original question. So here it says calculate the limit of this function. Now remember, if we're going to apply L'Hopital's rule, our function needs to be able to be written as a quotient like that, something divided by the other, and it's not at the moment, so we need to change it so it looks like that, and we can use the definitions for cosec and cot and write them as fractions. So from pure 2, you would have learned that cosec is 1 over sine x, and cot is 1 over tan. Actually, yeah, it's 1 over tan. Now I may change that in a minute because I want to write this as a single fraction. So another way of thinking of cot is cos over sine. So I could have gone straight from here and written that as cos over sine, but let's do that now. So the limit as x tends to 0 is 1 over sine x minus cos over sine x, or cos x over sine x. And I need to do that because I need to write it as a single fraction. So now I get it in the correct form, which would be 1 minus cos x over sine x. Right, so it's in the right form. Now we need to determine whether it's indeterminate. So we're going to look at the limits of the numerator and the denominator. So let's start with the numerator. So that would be the limit of 1 minus cos x as x tends to 0. So that will be 1 minus cos 0, which is 1 minus 1, which is 0. So the top is indeterminate. The numerator, let's do the same with the denominator. So the limit as x tends to 0 of sine x. So that will be sine 0, and sine 0 is 0. Okay, so this is indeterminate. Okay, so since the limit of x tends to 0 of, and the original question is this, cosec x minus cot x equals 0 over 0, it is indeterminate. So we can use L'Hopital's rule, which is what we'll do now. So always do that check. Right, so that means we're taking this and we're differentiating the top and we're differentiating the bottom of it. So now the question becomes the limit as x tends to 0 of, well, we need to work out what 1 minus cos x differentiated. That's just going to be sine x. And then the denominator here, sine x differentiated, just become cos x. Let's write cos x here. Right, now let's consider the numerator and the denominator and see if they're indeterminate or not. So the limit as x tends to 0 of sine x is sine 0, which is 0. Okay, so get 0 at the top. Now, if the bottom also gives us 0, it's indeterminate, and then we'd have to apply L'Hopital's rule again. Let's see what happens. So the limit as x tends to 0 for cos x will be cos 0. Now that's actually 1. So the actual whole expression becomes 0 over 1, which is 0. So it's not indeterminate. If it was 0 over 0, it would be. So the limit as x tends to 0 of the original question, which was cosec x minus cot x, equals 0. There's our final limit there. Okay, so this question says use the relationship t equals e to the log t. That's basically like a substitution. So I'll just put that down. That's going to be a substitution that we make to calculate this limit here. Okay, so let's start by saying let t equal to this part here. That seems to make sense. Yeah, so let t equal to that whole thing we're trying to find the limit of, which is 1 plus a over x to the power x. So if we let t equal to that, that means that actually we have e to the log and that 1 plus a over x to the power x there. So what does that mean? Well, if we look at the original question, which is finding the limit of this 1 plus a over x to the power x, that can be written as the limit as x tends to infinity of e to the log 1 plus a over x to the power x. Yeah, because we know that these would cancel down, yeah, which we're not going to do because we'll end up back where we started. But yeah, those two are equal. Right, now there was a rule that was mentioned on the first slide. I'll just write it down here. And this rule said this, that if you have the limit as x tends to a of e to a function, we can slip that limit part in here and actually write it as e to the limit, or as x tends to a, of that function. Okay, so we're now going to apply that rule. So we're basically going to slip in this limit and put it here. So using that rule, which we can just state without any proof, that the question now becomes e to the limit as x tends to infinity of the log of this 1 plus a over x to the power x. Now we're only, from this point on till the end, we're only going to be looking at this part here. So we're going to evaluate this limit. But we won't forget about the e, and then at the very end our answer is going to be e to the power of something, and that power is going to be whatever limit we've worked out that bit in the green cloud is. So once we've evaluated this and worked it out, I don't know, let's say that this is 10, I'm just making up a number, then our final answer will be e to the power of 10. So now let's evaluate that limit. So let's write it down. So the limit as x tends to infinity of log 1 plus a over x to the power x. Now the first thing we can do is use the rules of logs, which say if you've got a power, that power can be written at the front. Yeah, because our whole aim is we're probably going to be applying L'Hopital's rule, and we want this written as just one function over another, which we haven't got at the moment. So this becomes the limit as x tends to infinity of x log 1 plus a over x. Now we want a quotient, and we haven't got a quotient at the moment, we've got a product, we've got two things multiply together. And multiplying by x is the same as dividing by 1 over x. So we can bring our quotient in. Yeah, so the next step now would be to write this as this, the limit as x tends to infinity of log 1 plus a over x divided by 1 over x. Okay, so here's our quotient. We've got it in that form, one function over another. So now we're going to see if either or both of these limits are indeterminate, or whether we can evaluate the limit directly. Okay, so let's look at the top. So log of 1 plus a over x, and we're evaluating, well, what's this limit as x tends to infinity? Okay, well, as x tends to infinity, okay, this will basically become 0. Yeah, it doesn't matter what we've got at the top. You're dividing by a bigger and bigger number, it will tend to 0. So what we'll end up with is log 1, which will be 0. So the top is indeterminate. And the bottom, if we look at the limit as x tends to infinity of 1 over x, this is one we should know, that becomes 1 over 0. Sorry, not 1 over 0. It tends to infinity. That is also going to tend to 0 as well. Okay, so the whole thing is indeterminate because we end up with 0 over 0. So since the limit as x tends to infinity of log 1 plus a over x over 1 over x equals 0, 0. It's indeterminate, so I'll just put we can apply L'Hopital's rule, which means we need to differentiate the top and the bottom. So we need to differentiate, let's just highlight it. We're going to differentiate this log 1 plus a over x, and we're going to differentiate this 1 over x. Right, so applying his rule, we're now going to work out, hopefully, the limit of these first derivatives. Now, if I want to find the log of something, and I'll write it up here as a reminder. So if I want to differentiate the log of a function, so if y equals that, then dy dx is equal to the function differentiated over the function. Okay, so we'll use that to differentiate the top part. So the top differentiated is going to be a fraction, so it's going to be something over 1 plus a over x, and if you differentiate 1 plus a over x, that just becomes negative ax to the minus 2, because a over x is like ax to the minus 1. And then if we differentiate the bottom, 1 over x differentiated becomes negative x to the minus 2, like this. Now this will cancel down, but it may be more obvious if I write it slightly differently. So if I take this top part here, if I write that as negative a over x squared, that might be a bit more helpful. So I'll write the top as 1 over 1 plus a over x times by negative a over x squared. So I've just written it slightly differently. I'm going to do the same for the denominator, and I'll write that as negative 1 over x squared, like this. Yeah. Now you'll see the cancelling down a lot more easily. These two terms are almost the same apart from just the a. So what will happen with the cancelling down is that basically all of this will cancel down with all of this here, just leaving the a. So what I'm left with is trying to evaluate this limit, and that is just 1 over 1 plus a over x. Whoops, I just left off my a there. That should be a at the top. Yeah, so I'd forgotten about that poor little a there. So let's put that back. Right, so yeah, now let's evaluate this limit. So as x tends to infinity, this will become 0. So actually all this becomes is just a over 1. It just becomes a, because this will tend to 0 as x tends to infinity. So 1 plus 0 is 1. A over 1 is just a. Now remember, this that we worked out is just this. All of that was just to evaluate that limit. So we're not quite finished. Yeah, you could be tempted to write that down as your answer, but remember, that was the limit we evaluated. That was the power of e. So all of that working, we worked out that this limit here is a. So our final answer would be e to the a. So we'll finish this off by saying, so the limit as x tends to infinity of 1 plus a to the x to the power x is e to the a. So that will be our final result down here. So you should now be able to do exercise 7b on pages 155 to 156. So just as a quick recap, we've been looking at L'Hopital's rule that allows us to evaluate limits. So we can evaluate limits here, and we can evaluate limits if the question is of this form, one function over another, like this, and also that needs to be indeterminate. So in other words, if we were to evaluate that limit, we would get 0 over 0, or plus or minus infinity over plus or minus infinity. So if those two things apply, and we can differentiate it as well, differentiate. I'll just put differentiate there. If it's differentiable, then we can apply L'Hopital's rule, and his rule says, right, that this limit is going to be the limit of the derivatives divided by each other. And if this is indeterminate, you could almost do it as a flow chart, couldn't you? So if this is indeterminate, so basically we get that or that again, we can apply his rule a second time and work out this limit. And I'm guessing if that was indeterminate, we could apply it a third time. And if that was indeterminate, we could apply it a third time. Yeah, but make sure when you do these questions, show that you have tested to see if f of x over g of x is indeterminate. Okay, you must show that you've actually shown that it's 0, 0, 0 or infinity over infinity.